Hi everyone. So up till now we have completed 3 lectures. Lecture number 3 we have completed in the last class. So in this class we are going to start lecture number 4, and we are dealing with the third chapter, that is coordinate systems. So in this we are going to continue. In the last lecture itself we have started the rectangular coordinate system. So in this lecture also we will continue this rectangular coordinate system. So in the previous lecture we have seen what do we mean by the position vector, right, and what are these direction of cosines. So all these things we have seen in the previous lecture. So in this lecture we will see or we will study about the differential lengths. What are the differential lengths in rectangular coordinate system, and then differential areas. What are the differential areas, and differential volume. What is the differential volume? Okay. So determining these parameters is very important. In all the coordinate systems here, not only in rectangular. So even if we go for cylindrical, and then for in a spherical coordinate system also, this differential lengths and differential areas and differential volume are very important. Okay. So these are going to be helpful here. These are going to be very much helpful as we proceed into the subject. So first of all, you have to get the deep understanding of this differential lengths, differential areas and differential volumes. So once you understand these things in a crystal clear manner, then as we proceed into the subject, you don't feel any difficulty. Understood? Okay. So these are going to form a strong foundation for you, right? Okay. So see here. So I'm moving on to the next page, right? So here I'm considering this as a x-axis, and this is y-axis, and this is z-axis, right? Okay. So this is x-axis, and this is y-axis, and this is z-axis, right? Okay. So we will see what are the differential lengths, and what are the differential areas, and what are the differential volumes, right? Okay. So now see here. Now if I consider a small differential length here, if I consider a small differential length along x, I am considering a small differential length, infinitesimally very small differential length along x, so that I can represent it as dx, right? And this small differential length dx is pointing in which direction? It is pointing in x direction. Okay. So what is the unit vector along x here? The unit vector along x is nothing but what? Ax cap. So this is the small differential length along x direction, that is dx ax cap. So dx is the small differential length, ax cap will give you the direction of that small differential length. So that is along x direction, right? Okay. So now similarly, if I consider a small differential length along y, I am considering a small differential length along y. So that I can represent it as what? So the small differential length along y, I can represent it as dy into what? Into ay cap. So dy is the small differential length. Ay cap will give you the direction of what? The direction of this small differential length. Understood? Okay. So next, similarly I can consider a small differential length. Along what? Along z. So this I can represent it as dz into what? Dz into az cap, right? So let us consider this is origin, right? Okay. So what are the differential lengths in a rectangular coordinate system here? We got 3 differential lengths. One is what? One is dx ax cap, and another one is what? Another one is dy ay cap, and another one is what? dz az cap. So these are the small differential lengths we got in what here? In rectangular coordinate system. See, if suppose if I consider some point here, if I consider some point in 3-dimensional space, so this point is lying somewhere here. Understood? It is not in YZ plane, it is somewhere here. Let us assume it is somewhere here. Okay, so then if you draw a parallel line to x-axis, a small differential length. Okay, so here also this represents what? Dx ax cap, right? So if I small differential length parallel to y-axis, so that I can call it as what? Dy ay cap. So if I draw a small differential length that is parallel to z-axis, so that I can call it as what? Dz az cap. Understood? Okay, so in general the small differential length that is parallel to x-axis, we can call it as what? Dx ax cap. A small differential length that is parallel to y-axis is nothing but dy ay cap. A small differential length that is parallel to z-axis, we can call it as dz az cap. Understood? Okay, okay. So these are the 3 small differential lengths along x, y and z, right? Okay. Now if I consider a small differential length which is neither along x nor along y nor along z. So if I consider some small differential length like this, okay, so let us say this is dl bar, let us say this is dl bar. So this dl bar is neither along x nor along y nor along z, so it is pointing somewhere like this. Understood? Okay, so that dl bar, how you can represent here? The small differential length dl bar is neither along x nor along y nor along z, which means that the small differential length dl bar is going to have its components along those reference axes. So that we can represent it as what? Dl bar is equivalent to what? Is equivalent to dx ax cap plus what? Plus dy ay cap plus what? Plus dz az cap. So in this manner we can represent the small differential length which is neither along our reference axis. Understood? Okay, okay, fine, right? So if we know the differential lengths, then we can easily determine what? We can easily determine this differential length which is neither along x nor y nor z. Understood? Okay, okay. So similarly, see, this is very important here. Just we have to know what are the differential lengths along x, along y, along z. Okay, so these are very important, these 3, right? Okay, so now with the help of these 3 differential lengths, how many differential areas we can form? Tell me. See, already I have told that if you do a bar cross b bar, that means if you do the cross product between any 2 vectors, that is going to give you what? That is going to give you the surface area formed by these 2 vectors, right? And the direction of the surface area is given by the unit normal drawn to that surface, right? Okay, so that means if you do the cross product between any 2 vectors, that is going to give you what? That is going to give you the surface area formed by those 2 vectors. Understood? Now here, how many vectors you are having? Small differential vectors. How many small differential vectors we are having? Here 1, 2, 3. So with the help of these 3 small differential vectors, or I can say with the help of these 3 small differential lengths, how many differential areas we can form? Tell me. See, if you take dx dy, okay, so if you do the cross product between dx ax cap and dy ay cap, so you are going to get what? Whenever you are doing the cross product, it is going to give you what? It is going to give you the surface area formed by dx and dy. Understood? Okay, so similarly, if you do the cross product between dy ay cap and dz az cap, you are going to get another differential area. And similarly, if you do the cross product between dz az cap and dx ax cap, you are going to get another differential area. So totally how many differential areas can be formed here? 3 differential areas can be formed. Understood? Okay, okay. So the first differential area, so the first one I am writing here, right? Okay, so dA1, the small differential area dA1 is equivalent to, I am doing the cross product between these 2. So what you are going to get? Dx ax cap cross what? Cross dy ay cap. So what you are going to get here? So dx ax cap cross dy ay cap. So what is the magnitude? Magnitude is nothing but dx into dy. So what is the direction? Direction is nothing, is given by what? Ax cap cross Ay cap. We know that Ax cap cross Ay cap is nothing but what? Az cap. So here you are going to get Az cap. So this dx dy represents the small differential area in which plane? In xy plane. And what is the direction of this small differential area? The direction of this small differential area is given by what? Is given by unit normal drawn to this area. So if you draw the unit normal to this surface area, it is going to point in which direction? Az cap direction. So here dx dy. So this is xy plane here. So let us say this is dx, right? And I am drawing a parallel to y. So let us say this is dy. So this is nothing but what? If you multiply these two, you are going to get dx dy. So if you draw a normal, to this plane, it is going to point in which direction? It is pointing in Az cap direction. So this is the small differential area we got. Here we have done dx Ax cap cross dy Ay cap. So that's why we got the direction of the surface as Az cap, right? Okay. So now here in this plane, what are the variables here? X is variable and y is variable. So which means z is what? Z is constant. Understood? So we can call this plane as what? We can call this plane as z is equal to constant plane. We call this plane as what here? Z equal to constant plane. And if you observe, for z equal to constant plane, what is the direction of the surface here? We can call it as z equal to constant plane, or you can call it as z equal to constant surface. Understood? So for z equal to constant plane, what is its direction? Its direction is along what? Is along Az cap. Understood? So remember this point. For z equal to constant plane, the direction is along Az cap. Right? And here you are enclosing the surface from dx Ax cap to dy Ay cap, from x to y. Right? Okay. Fine. Right. Next, see here. So now okay. Now if I want the total surface area here, right, on xy plane, suppose I have given the range of x. The range of x is varying from x1 to x2. I have given the range of x is varying from x1 to x2 in xy plane, right? And I have given the range of y is varying from y1 to y2. And if I ask you to determine what is this surface area, then what you have to do? So this is in xy plane, so the variables are nothing but x and y. Understood? Okay. So if you want the total surface area, what you have to do? You have to integrate on both sides. This is the small differential area in xy plane. So if you want the total surface area formed by the ranges of x and y, then what you have to do? You have to integrate with respect to x from x1 to x2, and you have to integrate with respect to y from y1 to y2. Then you are going to get the total surface area formed by these ranges. Understood? Okay. So if you want the total surface area, so then I can write it as A1. Okay. So the total surface area A1 bar is equivalent to what? You have to integrate with respect to x. X is varying from x1 to x2, and also you have to integrate with respect to y. Y is varying from where to where? y1 to y2, dx dy az cap, dx dy az cap. So if you do this, what you are going to get? You are going to get x2 minus x1 into y2 minus y1 into what? Into az cap, into az cap. So x2 minus x1 into y2 minus y1. So this is the total surface area we got within this range. Okay. So what is the shape of this surface area here? So x2 minus x1 is just like a length, and y2 minus y1 is just like a breadth. Okay. So length into breadth, you will get what? You will get the surface area of a rectangle. Understood? Okay. Surface area of a rectangle in xy plane, right? Okay. So here the shape of the surface here, the shape of the surface, you are going to get what? You are going to get a rectangle. You are going to get a rectangle. Understood? So if you vary x and y in xy plane, okay, what is the surface area you are going to get? You are going to get the surface area of a rectangle in the xy plane, right? Okay. Since here you are enclosing from x to y, you are enclosing the surface from x to y, the direction of the surface is in az cap direction. Understood? Okay. Okay. So this is one small differential area, which is nothing but what? Which is nothing but z equal to constant plane, right? Okay. So similarly we can determine another differential area. See, always write down the differential lengths here. If you write down the differential lengths, then you can easily determine, or you can easily analyze each and everything, right? Okay. So what is next differential area here? So dA2 bar is equivalent to, now I am doing the cross product between y and z. So you are going to get dy ay cap cross what? Cross dz az cap. So this is equivalent to what here? You are going to get the magnitude is dy into dz. What is the direction? Ay cap cross az cap is nothing but what? Is nothing but ax cap. So this is the small differential area. So here the variables are nothing but y and z. That means x is constant. So we can call this plane as what here? X is equal to constant plane. X is equal to constant plane. So remember that for x equal to constant plane, its direction is along which direction? Its direction is along ax cap direction. Understood? Okay. So now, what is the total surface area here? If you want the total surface area, you have to integrate with respect to what? With respect to y and with respect to z. So if you do this, you are going to get what? You are going to get the total surface area. So let us say y is varying from y1 to y2 and z is varying from z1 to z2. So if you do this, what you are going to get? y2 minus y1 into what? Into z2 minus z1 into what? Into ax cap. So what is the shape of the surface here? Here also the shape of the surface is nothing but what? Is nothing but a rectangle in which plane? In yz plane, right? Okay. So this is another differential area, right? Okay. Next, what is left out here? Next, if you do the cross product between dz az cap and dx ax cap, you are going to get another differential area, right? So that differential area I am calling it as dA3. So which is equivalent to what? Which is equivalent to dz az cap cross what? Cross dx ax cap. So what you are going to get? The magnitude is dz into dx. Az cap cross ax cap is nothing but what? Is nothing but ay cap, right? Okay. So here the variables are nothing but what? Z and x. The variables are nothing but z and x. So y is constant. So this plane is called as what here? Y equal to constant plane. Y equal to constant plane. So for y equal to constant plane, what is its direction? Ay cap. So when it will be ay cap? Whenever you are enclosing the surface from where to where? From z to what? From z to x. Understood? Okay. If you enclose the surface from x to z here, if you enclose the surface from x to z, then what you are going to get? Here you are going to get minus ay cap. Understood? Okay. So keep these points in mind, right? Next, what is the total surface area here? So if you want the total surface area, what you have to do? You have to integrate with respect to z and with respect to x. So integration with respect to z, let us say z is varying from z1 to z2 and x is varying from x1 to x2. So dz dx ay cap. Okay. So if you do this integration, what you are going to get? You are going to get z2 minus z1 into what? Into x2 minus x1 into what? Into ay cap. So what is the shape of this surface here? The shape of this surface is also what? Is also a rectangle. Rectangle in which plane? In zx plane, right? So with the help of three differential lengths in rectangular coordinate system, we can form three differential areas. So all these three differential areas are nothing but what? Are nothing but rectangles only. Okay. So all the three differential areas are all the three surface areas in this rectangular coordinate system are nothing but what? Are nothing but rectangles only. So we got three surface areas here. One is z equal to constant plane, another one is y equal to constant plane, and another one is x equal to constant plane. So all these planes, what is the shape of all these planes here is nothing but a rectangle. So the shape of all the three surfaces in rectangular coordinate system are nothing but what? Are nothing but rectangles, right? Okay. Okay. So here we have forgot one thing. So that is you know that I think you know this one. So that is the range of x, the range of y, and the range of z. So what is the general range of x here? What is the general range of x? So it can vary from where to where? It can vary from minus infinity to what? Minus infinity to plus infinity. So x can take any value from minus infinity to plus infinity. So this is the range of x. So similarly, what is the range of y here? Its range is from minus infinity to what? Minus infinity to plus infinity. And what is the range of z here? The range of z is also from minus infinity to plus infinity. Okay. So I hope you know these things here, right? This is the range of x, y, and z in rectangular coordinate system. So 1 minute here. Okay. Okay. Next. Okay. So this is the range of x, y, and z, right? So we have seen about differential areas. Next we will see about differential volume. So we will see how to determine this differential volume, right? Now see here. Let us consider, I am considering a small differential length dx, right, and I am considering a small differential length dy. So if I multiply these two, okay, sorry. So if I multiply these two, what you are going to get? You are going to get this surface area. This is small differential area you are going to get, right? Okay. Okay. Now if I extend this surface here, if I extend this surface in its perpendicular direction, see what is its perpendicular direction? If you draw the perpendicular to this plane, it is going to point in which direction? Z direction. Understood? So if I extend this plane in its perpendicular direction by dz units, so like this one, see here I am extending this surface along z direction, by how many units here? By dz units. Okay. So I am extending this surface by dz units. By dz units in z direction. So that means if I multiply with dz here, this surface is what? Dx into dy. Understood? Now I am extending this surface along z direction by dz units. So if you do that, what you are going to get? You are going to get this volume or not? Yes or no here? You are going to get this volume. So what is this volume here? This volume is, I am representing with small differential. This is the volume, right? Okay. So this is the volume you are going to get. Okay. So this volume I am representing with dV, which is equivalent to what? Which is equivalent to dx dy into dz. Dx dy into dz. Okay. So this is the small differential volume that you are going to get. So actually how we are getting this one? See here. So first what we have taken here? We have taken a surface. Okay, that is formed by dx and dy. So that is we know how to form the surface with the help of two vectors. So that is nothing but dx ax cap cross what? Cross dy ay cap. So this is going to give you the small differential area formed by dx and dy. Now what we have done here? What we have done? We have extended this surface. We have extended this surface along z direction by dz units. Understood? So that means we have multiplied, you have to multiply this surface with what? With dz, with dz. Understood? You have extended this surface along z direction by dz units. That is along which direction here? Az cap direction. That is dz into az cap. Understood? Okay. Now this is a vector. This is also a vector. Understood? So the resultant of this one, dx ax cap cross dy ay cap, the resultant of this one is nothing but what? Is nothing but a vector quantity. And this is also nothing but what? Vector quantity. Understood? Now you have to multiply these two. Right. So now here you have to do dot product or you have to do cross product. Which one you have to choose? Tell me here, which one you have to choose? See here, dx ax cap cross dy ay cap, what you are going to get? Dx into dy ax cap cross ay cap is nothing but what? Az cap. Understood? Okay. So now you are extending this surface along z direction by dz units, okay, along z direction. Right. Okay. So now if you do the cross product here, what you are going to get? Az cap cross az cap will become 0. That means the volume you are getting as 0, which is wrong. Right. Okay. So what you have to put here? It must be dot product. It must be dot product. Right. Okay. Okay. So that means here take the surface and extend. If you want to extend the surface, you are extending this surface in a direction perpendicular to this surface by dz units. So that is dz az cap. So what you have to do? You have to do the dot product between these two. So if you do the dot product between these two, what you are going to get? Dx dy az cap dot dz az cap dot az cap will be 1. So what you are going to get? Dx into dy into dz. So this we call it as what? Differential volume. So this is how you are getting the differential volume, dx dy into dz. And this differential volume is the resultant of what? The resultant of this dot product. And we know that the resultant of dot product is nothing but what? Is nothing but a scalar quantity. So this differential volume is what? The volume is a scalar quantity. So this is what we have seen while telling the examples for scalar quantities. Right. So in the previous lectures, in the first lecture, I think in the first lecture itself, I have given the examples for scalar quantities. There I have told the surface area is a vector quantity, whereas volume is a scalar quantity. Understood? Okay. Okay. So here is the proof. Right. Okay. So the resultant of this dot product is nothing but what? Is nothing but a scalar quantity. Right. Okay. So now this is the differential volume. This is the story of differential volume. So the differential volume dV is equal to dx dy into dz. Okay. So now if they ask to determine the volume formed by the range of x, range of y and range of z. Suppose they have given x is varying from x1 to x2 and y is varying from y1 to y2 and z is varying from z1 to z2. Suppose they have given like this. Right. Okay. And if they ask us to determine the total volume, so in order to determine the total volume, what you have to do? You have to integrate with respect to x, with respect to y, with respect to z over their ranges. Understood? So total volume V is equivalent to what? Integral with respect to x, integration with respect to y, integration with respect to z. So x is varying from x1 to x2, y is varying from y1 to y2, z is varying from z1 to z2. So dx dy dz. So this is equivalent to what? What you are going to get? You are going to get x2 minus x1 into y2 minus y1 into what? Into z2 minus z1. So this is the volume you are going to get. So what is the shape of this volume here? What is the shape of this volume? The shape of this volume you can easily guess here. Okay. So x2 minus x1, draw a line that is parallel to x axis, draw a line that is parallel to y axis, draw a line that is parallel to z axis. So it is just like length into breadth into height. So what you are going to get? You are going to get the volume of what? The volume of a cube. Understood? Okay, so this represents, the shape is nothing but what? The shape is nothing but a cube here. The shape is nothing but, the shape of the volume is nothing but cube. Understood? Okay, okay. So what we have concluded here is in rectangular coordinate system, the differential lengths are nothing but dx ax cap, dy ay cap, and dz az cap. With the help of these three differential lengths, we can form three differential areas, and the shape of those surface areas are nothing but what? Are nothing but rectangles. Understood? So we can form three surface areas. So that is z equal to constant plane, y equal to constant plane, and x equal to constant plane. So all the shapes of these surfaces are nothing but what? Are nothing but rectangles, right? Then by taking a small differential area and extending that small differential area in its perpendicular direction, okay, we are going to get the volume. We are going to get the volume, a small differential volume. So that dV is equivalent to what? Dx ax cap cross dy ay cap dot dz az cap. Understood? So we are going to get it as dx dy into dz. So volume is a scalar quantity because it is the resultant of the cross dot product, right? Okay. Okay, so these are the things we have seen, and also we have seen that if you substitute the range of x, y, and z, the shape of the volume you are going to get here is nothing but a cube, right? Okay, okay. So I hope all these points are crystal clear here. I hope all these points are crystal clear. See, as we proceed into the subject, here just we are learning what are these differential lengths, differential areas, differential volumes, and all these things. Okay, just we are putting some foundation, mathematical foundation, in order to understand the subject here. Okay, so as we proceed into the subject, we are going to see the applications of these coordinate systems and all those things, right? Okay, okay. Here just we will study about these differential lengths, differential areas, and differential volumes. Its applications we are going to see in the subject. Understood? Okay, okay. So always remember one point here. Here we are just building up some mathematical foundation in order to understand the subject. That's it. Okay, so there is no need for us to go in depth into the mathematics. Okay, that you will do in mathematics subjects, not here. Okay, so here just we are putting some foundation of some basic mathematics that is needed for us to understand the subject in a crystal clear manner, right? Okay, okay. So once we get familiar with this mathematical language, then you can enjoy the movie of EMT, right? Okay, okay, fine. So with this I am ending up this lecture here. So with this I am ending up this lecture, right? Okay, okay. So this is the end of this lecture. Right? Okay. This is the end of this lecture, and in the next lecture we are going to start a cylindrical coordinate system. So with this, rectangular coordinate system is completed. So in the next lecture we are going to start a cylindrical coordinate system. This is enough here. This is more than enough. Whatever we have studied up till now, that is more than enough for rectangular coordinate system. So you can easily understand this rectangular coordinate system. Understood? Okay, it is not that much difficult. Okay, even cylindrical coordinate system and spherical coordinate system also I will make you to understand in a crystal clear manner. It is also very simple here. Just if you understand the concept and basic things, then you can easily understand the cylindrical and spherical coordinate systems also, right? Okay, but with this lecture I am ending up this rectangular coordinate system, and in the next lecture we will see cylindrical coordinate system, and after that we will see spherical coordinate system, right? Okay, okay. So I hope up till now it is crystal clear, right? Okay, okay. So thank you for watching. So take care. Bye bye.